In this video, we're going to cover the differences between distance and displacement, along with a few examples of how to calculate them. For those who don't know me, my name is Chris Inazoni. I've been tutoring for about 2 years now, and I make these videos so that VC students can do the best they can in math methods. With that out of the way, let's get into it. The position of some object or particle is often depicted on a graph like this. Position graphs are often expressed as some function x of t, where, oddly enough, x is on the y-axis and t goes on the x-axis. This is because x tends to be a stand-in for position. A position graph simply tells you how far away a particle is from the origin for a given time value. For example, if this graph was in terms of meters and seconds, then we could say that after 2 seconds have passed, the particle has gone 4 meters away from the origin. More specifically, when it comes to position, we tend to express position as if it were left or right of the origin, where positive position values are right of the origin and negative position values are left of the origin. So the most accurate way of describing this situation is to say that the particle has moved 4 meters to the left of the origin. Yes, I know the graph is saying up and down, but this convention of saying positive is right and negative is left comes from the x-y axis convention. We tend to borrow that when we describe the position of the particle. So a big part of this area of study is figuring out what your position graph is actually telling you about the real-world situation of the particle. Speaking of real-world scenarios, it's worth highlighting that only t values that are greater than or equal to 0 are defined for this graph. This is because t is a substitute for time, and negative time values just don't really make sense a lot of the time. A very common question to ask is, what is the initial position of the particle? Now, initial anything just means what happens at t equals 0. So initial position just means what is my position at t equals 0. And in this case, when you sub in t equals 0, you actually get a position of 0 as well. So this would be interpreted by saying that at t equals 0, the particle is at the origin. Or even more succinctly, the particle starts at the origin. If your position is positive, then it means that your particle is located to the right of the origin. In this case, if we sub in t equals 0, we can see that our initial position is going to be 4 meters to the right of the origin. If we were to plot the actual path of the particle, it would look something like this. In this case, position is on the x-axis and the time is just implied. Graphs like these are very limited because all you can see from them is the direction that the particle is moving, but they show up in the books anyway, so you need to be familiar with them. Anyway, let's plug in some values to get an idea of what's going on. At t equals 0, we are 4 units away from the origin. At t equals 1, we're 5 units away from the origin. And at t equals 2, we are 8 units away from the origin. We can see this pattern is always trending away from the origin, headed towards the right. So you can see the information that this kind of graph has is limited. There is no time information in the path graph. This is why we tend to prefer to use position graphs instead. If your position is negative, it means that you're located to the left of the origin. In this case, when we sub in t equals 0, we're going to get negative 4 as a result. Hence, our particle is located 4 units to the left of the origin. If we were to plot this path of the particle, then it would look something like this. At t equals 0, we can see that we start 4 units to the left of the origin. At t equals 1, we can see that it's gone down to 3 units to the left. And then at t equals 2, we can see that we end up at the origin. Position is defined differently to distance. Position only cares about the difference between the starting point and the ending point. Distance, however, cares about the entire length of the journey. Consider the case where we are running a 1 kilometer race around an oval. When you run the race, you start and end at the exact same spot. Hence, your displacement for the journey would be considered 0. However, the distance that you traveled for the journey would be considered 1 kilometer. Depending on the graph, distance and displacement might be the same thing. We'll look at a couple of examples, one where they're different and one where they're the same. The best way to handle these kinds of questions is to just start by drawing a graph of your position equation. I've cut mine off to end at 5 seconds. To find the displacement, we just need to know where did we start and where did we end. And we can do that by subbing in t equals 0 and t equals 5 into our position equations to get the positions at those spots. All we do here is subtract the start from the end, giving us a total displacement of negative 5 units. Nice and simple. If we instead want distance, then we have to consider turning points in the graph. A turning point on the graph indicates that your particle has changed direction. And so to account for this, we're going to count distance in 2 stages. First, we're going to find the distance between the start and the turning point. We do this the exact same way as before. We find the positions at those spots and then subtract the start from the end. This gives us a net distance of 9 units. We're dropping the negative sign because distance doesn't care about direction. 9 meters is 9 meters. Once we have the first distance, we're now going to calculate the second distance, which goes from the turning point to the end point. We use the same method here. Now we just add those two results together, giving us a total distance of 13 units. So now we're going to solve the exact same equation, but this time only doing it over the first 2 seconds. Starting with displacement, we're just going to do the same thing as before. We need to know where we're starting, where do we end, subtract the two things together, and in this case, that's going to give us a displacement of -8 units. When it comes to distance, we would have to have a look for turning points. But in this case, there are no turning points on that interval from 0 to 2. So it turns out that our distance equation is going to look identical to that of the displacement equation. The major difference is that we're going to knock off the negative sign because, once again, distance doesn't care about direction. So negative signs are no longer valid for distance. So I guess it's not strictly true to say that distance and displacement are identical in this scenario, the only major difference there being the fact that distance can never be negative. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.